All right. So when you come back from spring break on Tuesday, March 25th, hopefully you're back on Monday for your Monday classes, but what do I care? I teach on Tuesdays. So when you come back on Tuesday, you'll have homework 8 finished, and then the following class period on the 27th is when your draft submissions for the pipe network sizing. So remember, what I'd like you to do on that assignment is upload 2 PDFs, 11 by 17 paper size, that has your annotated map, and the annotations should include the junction name, the pressure at each junction, the pipe length, the pipe diameter, reservoir elevation, the water surface elevation of the reservoir, and the reservoir's location. So, any questions that have come up as you're working on the project? The homework? What's that? Is that homework 9? Did you turn in homework 8 last time? What did I just return to you? Okay, so I've got the numbering wrong. Thanks for pointing that out. So this is homework number 9. Thank you. All right. Well, that'll work out perfectly as long as it's chapter 12, problems 1, 2, 7, and 10. Yeah. All right. So today we're going to be talking about, in Chapter 12, discharge-depth relationships, transition in channel beds, and chokes. All right, so it's some good stuff that starts with another look at the specific energy versus depth of flow. So this is what we sort of left off with last time, is the idea that for a certain amount of specific energy, there are 2 different depths, or alternate depths as they're known, where you can either have supercritical flow or subcritical flow, but the total energy is the same. And so, who remembers, if this farthest leftmost point is the dividing line, if this is where we've got critical flow, and all of the diagrams look like this, by the way, regardless of the cross-section or the flow rate, the general shape of a specific energy diagram is always this sort of sideways curve. So, that said, what region is subcritical flow and which region is supercritical flow? Bottom. So the bottom is supercritical flow, and why is that? That this region below the critical depth, so below down in here, all of these depths are supercritical. Why? Because that's the one that's associated with higher speed. So there's 2 different energy levels. The same energy level, 2 different depths. This depth, the deeper of the alternate depths, is the subcritical depth. The shallower of the 2 alternate depths is the supercritical depth, because it's the one that's associated with a higher velocity. And the interesting thing is that all of these different depth possibilities correspond to the same flow rate, the same n value, and the same channel geometry. And so how is it that we get a different depth if those 3 things are fixed? It's just by varying the slope. It's the channel slope. So you can have a really steep channel, and even if the channel's steep, it's still the same flow rate that's flowing through the channel. It's still the same roughness if it's made out of some certain material, and the width doesn't change, but you're going to have different depths and therefore different velocities. So any questions that came up as you sat and meditated and reflected on specific energy after Tuesday's class?
Those lines continue. Are they capped off there for a reason?
No.
Or will they continue?
They will continue. And the reason was that if we zoomed out further, then we'd sort of not be able to see down here where the action's happening. Yeah, because it gets linear beyond that. Yeah. Yep, so you could have it super steep and it would be even faster, or very, very shallow and it would maybe be very, very deep. So the curve continues. All right, so here's a different curve, and we won't see this one as much, which is a pity because it's equally important but maybe a little bit harder to understand. So let's try and figure out what this curve is showing us. Now, this is a curve for the same amount of specific energy, so constant specific energy, but what it's showing is on the x-axis different discharges, and on the y-axis it is depth. And so all of these are different flow rates, and the flow rate that is the highest flow rate, you can see the one that's furthest to the right, the highest flow rate is the one that corresponds to the critical depth for the same amount of specific energy. So let me see if I can explain. I put it this way. The critical flow is the most efficient in terms of getting the most flow for the same amount of energy. Let's look back to this one. Now, these are a bunch of different specific energies, but the same flow rate. So in this graph, flow rate is fixed, but specific energy varies. This graph is a graph of varying flow rate, but the same amount of energy. And so if you've only got, you think of energy as your currency. When it came to pressure, for example, that's how you get water to move from place to place, is by spending your energy. You know, if you've got a pressurized tank, it's that pressure that allows you to move the water from place to place. In the case of open channel flow, energy is how you get the water to move from place to place. And here, the way to get the most amount of water moving for the certain amount of specific energy is to have it flow at the critical depth. So you can have lots of different depths for the same amount of energy, because remember that energy has two terms. Specific energy has the depth component and v squared divided by 2g. And so there's an infinite number of combinations. You could have, you know, a deep depth and a small velocity head. You could have a lot of velocity head and a little bit of depth. But all of those combinations don't have the same flow rate if E is fixed. So this is fixed at the same amount of specific energy for all the points on this curve. And what we're seeing is that the critical depth is the one that we have the biggest flow rate. So I've stomped that into the ground. And it probably, for many of you, still doesn't really make intuitive sense, and it won't until you think about it more. Maybe when we do some calculations it'll start to sink in, but this is a concept that took a while for it really to make sense to me. But the implications of a curve like this is that the critical flow point happens to be where we've got the minimum specific energy for a certain discharge, and conversely, you know, we can think of it as vice versa, the maximum discharge for a certain amount of specific energy. Maximum discharge for the certain amount of specific energy. So E is the total energy level, and depth is only one of two components for total energy, for the specific energy. So remember, energy is the depth plus the velocity head. And so if we've got a certain amount of depth, then it's going to have also an accompanying amount of velocity head, and the energy will be the sum of the two. Let's look at it this way. Let's say that we've got a channel that we've got some initial depth, the water's flowing along the channel, and then there's a step downward. The reason that we talk about specific energy sometimes is to look at how is the water surface going to behave when there's a step down, like is pictured here. And the y1 is the depth before the step, y2 is the depth after the step, and we can calculate the critical depth. For a rectangular channel, does anybody remember that formula for calculating the critical depth that I almost didn't want to tell you last time in class? It was an abbreviated formula that makes it a little bit easier to calculate the critical depth. No, the Froude number equal to 1 is, that is the Froude number when you've got critical flow, but it's lowercase q squared divided by g to the 1/3 power. So why was it that I didn't necessarily want to tell you this shortcut? Only works for a rectangle, doesn't apply to a trapezoid. So, you could go astray really easily applying this formula. And flow per unit width, lowercase q, was the flow rate divided by the channel bottom b. And so we can calculate the critical depth, if this is a rectangular channel, using this formula. And the critical depth upstream and downstream of this step is going to be the same. You'll notice that there aren't two different critical depths. It's saying y sub c. It's not saying y sub c1 and y sub c2. Upstream and downstream of this drop, the critical depth is the same. So the first thing that we're going to look at is how does the energy behave when there is a bed transition in the form of a drop. And we want to find out what will be the new flow depth, what's y2, downstream of a drop. And we're going to apply the Froude number to help us solve that. So you'll know the conditions upstream, like the initial flow depth y1, you'd be given the velocity, or maybe you'd be given the channel dimensions and the flow rate. And so from that you could find the velocity. You calculate the Froude number using the formula that's provided there. And the first thing that you do is you assess the flow regime upstream to know whether it is supercritical or subcritical flow. And then you go to our old friend, the specific energy diagram, and plot that out. And so there's a little bit of a, there's a lot going on in this diagram, so let's step through it. The first thing is, and by the way, this is one of those animations that I spent, more than an hour on just to draw some little arrows. So really soak this in, because it was an investment of my time so that we could step through and say, starting with the known y1, you go over to the diagram and you find the initial depth on the specific energy diagram. You follow that down and intercept the energy axis. So you find out how much initial specific energy there was there, and then we're going up by the amount of the bed step. So this step down is sort of like it's gaining energy, because we were at some higher elevation, and there's going to be more specific energy once you step down off of that drop. The water is going to have more energy, and so E2, the amount of specific energy there is downstream of the drop, is however much there was upstream of the drop plus the delta Z. And so graphically what we do is we just move sideways up along the x-axis in the amount of delta Z. So delta Z is how much we go up. Our fourth step is we find out there's two different crossings at that energy level. And so our new depth is going to be one of those two depths. It's either going to be the supercritical depth or the subcritical depth. And the way that we know which one to pick is because we analyze the Froude number at the beginning of the problem. We found out maybe in this case it was, you can see y1 is greater than yc. So what does that tell us about whether it was subcritical flow or supercritical flow? We can tell just from the graphic that's provided whether it was sub or supercritical flow. This drawing is showing y1 is greater than y sub c. Therefore, the flow condition is subcritical. Why did you say it's subcritical? Because we're above the critical depth. So what that means is that the water is moving slower. If you think in terms of velocity, the water is moving slower than the velocity would be if it was at the critical depth. So it is subcritical. And if we just jump back to that slide from, that's in a different file that I've got those criteria. We're in part 2 of the course now, by the way. But if you go back to the notes from last time, you'll remember that the criteria for subcritical flow is the Froude number is less than 1, or that the flow depth is greater than the critical depth. And so if we have subcritical flow at 1, which we do because y1 is greater than yc, then that means that after the drop, the flow's still going to be subcritical. Well, we're talking about, if there's a waterfall, so after the waterfall, when it reestablishes its flow, yeah, it's still going to be, if it was subcritical upstream, it's going to be subcritical downstream. Yeah. And so what will be the new depth? So we had two possibilities. the lower one, this lower crossing of the energy level with the curve, this would be the supercritical depth. Here's the subcritical depth, and so we go over, and here's the Y2. So what we can say as a rule, here we had subcritical flow, and the drop down, did that make the water depth greater or less? Is the drop going to make it deeper or shallower downstream? Deeper, because what you can see is that obviously Y2 is bigger than Y1. So it's a cause and effect thing. If it had been supercritical flow, like if we looked at the drawing and Y1 was below the critical line, then what would have been the depth change if it had been supercritical upstream? It would have been shallower, because look at this. If this was our Y1, then our Y2 would have been a little bit lower than Y1. And so if we'd had supercritical flow, then the drop would make the depth even shallower. Yes? The other way we can diagnose this is Froude number is less than 1. And actually there's a few other things too. The other way is if the slope is less than the critical slope, then that, a shallow slope, or it's called actually, in the terms of slope, there's mild. If it is less than the critical slope, they call it a mild slope. What do you think they call it if the slope is steeper than the critical slope? Spicy? No, it's steep. I wish it was spicy, but it's steep. So there's mild and steep. Okay. We'll talk more about slopes.
The seeming to me that the water surface is changing.
It is. Yeah.
It is.
It's getting deeper.
Well, I mean, but I look.
It goes up. Not by a lot, but it gets deeper. And as Gil points out, because it's getting deeper, the velocity is going to go slower, right? Continuity is still honored, it's still valid, and so the water's going to slow down because it got deeper. It'll be forced to, just after the jump. So there isn't any flow backing up. They call that backwater, when there's something that's causing the water to sort of pile up. This is still steady flow. It's not uniform anymore, because we have downstream and upstream, there's different flow conditions. And so this is not uniform across the jump, but it is steady. It's not instant. Like there wouldn't be like a right angle to it. It's gradual. Yeah, that's a good question. Not usually. No, not usually. It's counterintuitive, and it's not something that you've probably seen with your own eyes before. But in the lab, we can sometimes make it happen so that it can be measured with those little pin gauges. But that's the best we can do, is measurable with pin gauges. That's one thing, but seeing it with your eyes would be more convincing, right? It gets deeper. What's going to even blow your mind more, well, I'll get to that, but there's something that seems even less intuitive than this that we'll get to in just a minute. All right, so it's counterintuitive, but at least it all makes sense from the diagram standpoint, right? If I gave you a quiz next week, I'll be here in our class time. I'll be talking about hydraulics. No, I won't. All right. Let's say if it was the week after, a perfect quiz question would be, use the diagram to explain how you'd find the downstream depth. And so what I want you to explain is that you could find how much specific energy there is for the upstream depth, and then you would increase the specific energy because of the bed drop. And so the delta Z is to the right. You get more energy, and then there would be two possible depths to choose from, and the one that you know is the correct depth is the one that was either subcritical or supercritical, maintaining the flow regime that you had upstream. All right. Any questions before we move on? All right. So let's do some calculations. We've got a drop where it is an 8-foot width and Q equals 30 cubic feet per second, and our drop is 1.2 feet. So what is the flow depth after the drop? So I was explaining this in terms of the diagram, but I'll solve it in terms of specific energy. I won't solve this graphically. How do we find the new flow depth? So the principle that we're going to apply is that the specific energy at 1 is equal to the specific energy at 2 plus or minus the delta Z, as the case may be. But just to start things off, let's draw our channel. We've got a Q of 30 CFS. Our depth is 3.5 feet. And we've got a bottom width of 8 feet. All right, and so we can calculate the Froude number. Why do I want to know the Froude number? Because we have to know whether it's subcritical or supercritical before the transition so that we can say whether it's going to be supercritical or subcritical after the transition. Okay, so it's 30 cubic feet per second squared. The top width is 8 feet, which is the same as the bottom width. G is 32.2 feet per second squared in the traditional units. And we've got a cross-sectional area. If we do 8 times 3.5, that's 28 square feet, and we cube the area. All of that to the 1/2 power. Okay, so the Froude number, 0.101. Therefore, the flow is subcritical, right? Subcritical flow. And the Froude number is unitless. And just for kicks, we could calculate the velocity at 1, Q divided by A1. And so we would get 1.071 feet per second is our upstream velocity. Okay, so now in the second part of the problem, what we're going to say is that the energy at 1 is equal to the energy at 2 and then minus the delta Z. Okay, so let's just take a look at how this fits together. We've got y1 plus v1 squared divided by 2g is equal to y2 plus q squared 2g a squared minus delta z. Why do you suppose that I've expressed the velocity head at 2 in terms of the flow rate instead of in terms of the velocity? Right. We don't know the depth, therefore we can't find the area, therefore we can't find the velocity. So velocity is unknown, and we already have y as our unknown here, so no reason to have two unknowns in the equation. We'll just express our unknowns in terms of y. So that's why I've made the switch there. Okay, so let's substitute in the known values here. We've got 3.5 feet is our depth upstream, and our velocity upstream is 1.071 feet per second, and that's squared, divided by 2g, 32.2 feet per second squared. Okay, y2 is unknown. I don't know what the depth downstream is going to be, plus 30 cubic feet per second squared divided by 2g and then a squared. How am I going to write a squared? Or a squared. 8 times y. So it'll be 8 times y 2 the depth at location 2, and that is squared because it was the velocity head formula here. So, and then minus 1.2 feet. Okay, so if I combine all of this together, that is 4.718. So let me move over to here and continue. It's 4.718 is equal to y squared, not y squared, y sub 2, meaning the depth at location 2, plus 0.2184 divided by y2 squared. And actually, 4.718, that's actually that plus the 1.2 if I move it back over. So let's make sure that's the case. I need to rewrite those brackets there. If you'd calculate along with me to make sure that this is right, the 3.5 plus 1.071 squared, 2 times 32.2. Yeah, so this is only 3.518, and then we're going to add the 1.2, and that's where 4.718 comes from. Okay. So depth, velocity head, and we're adding the bed drop to it. And so basically what we're saying is all of the energy there is at 1 plus the drop is equal to the energy at 2. So that makes sense, right? How much energy is there downstream? Well, the energy downstream is all of the energy that there was upstream plus the drop, because it's getting more energy from the drop. And so we have the velocity head, which was very small, the depth, and then adding the drop to it. And so this is all of the energy at 1 plus the drop is equal to the depth plus the velocity head. And so we can multiply each term by y2, and that goes to y2 cubed minus 4.718 y2 squared plus 0.2184 is equal to 0. Here? No. Yeah, every term multiplied by y squared. Yeah, so this one will turn into y2 cubed. This one will be 4.718 y2 squared. And then this will just be the number itself. So last time you assured me that the Casios are good at finding roots. Can they find cubic roots like this pretty easily? What we should get is that there are 3 possibilities, 3 possible flow depths. The flow depth at 2 can be either negative 0.211 feet, so that's one possible flow depth, or it could be 0.220 feet, or it could be 4.708 feet. So of those 3 possibilities, the first we can exclude is the negative flow depth. All right. Which one is it going to be? Is this drop going to make it shallower than the original depth? Because originally it was 3.5 feet. So is it going to go from 3.5 to 0.22, or is it going to go from 3.5 to 4.7? Why do we know that? Just because it seems more reasonable? Intuition? Yeah. So this one's the subcritical root, and this is the supercritical root. And we exclude the supercritical root because we found upstream the conditions were subcritical. And so if it was subcritical upstream, it's going to be subcritical downstream, and therefore this will be the flow depth because of that drop. All right. So we went from 3.5 to 4.708. Any questions about this example? Bed drop.
The other way going.
All right. Yeah, what about a step up? That's what you're wondering, yeah. All right. So what if we have a step instead of a drop? Well, let's look at this diagram. Remember, energy is the flow depth plus the velocity head. So in theory, if we assume that there's no energy loss because of this step up, and we'll just assume that for now. Later on, we will start to account for how transitions like this maybe have a so-called local loss. Later on, we'll deal with that, but you'll notice that the total energy line here, this imaginary line that's above the water surface, is constant. And so the idea is that even though you've got that step up, you didn't lose any energy. So it just goes somewhere. It's going somewhere different. So E1, the energy that we have upstream of the transition, is how much we've got available to push it up over that obstacle. Because the step up is an obstacle, and we can't make that unlimited tall and still have the flow go over it. And so what we have to look at is there enough energy at 1 to make it over that obstacle? Because what if it was like this? Let me take it to the extreme. You know, what if we had, this was our initial flow at 1, and then we want to have a jump like that. Is it going to be able to cram all of the flow into that small of a cross section? You know, is it going to maybe get a little bit shallower and then still be able to keep going? So the process that we're going to be going through is we're going to be looking at how much energy is there at 1 and how does that compare to like a maximum step that could be tolerated. What's the Z max? Because that didn't really come up here. There is no maximum step down. The water can flow down easily enough, but the step is a little bit more, it has limits in the way that the drop doesn't. So we've got a certain amount of energy that can push the flow over the step, and the specific energy changes, but the total energy doesn't change. So this TEL stands for total energy line. And so here, the amount of energy relative to the channel bottom is going to decrease. As you might expect, there's less energy at 1 than there was at 2. No, I said that wrong. There's less energy at 2 than there was at 1 because you've got a certain amount of energy at 1, and then that delta Z is the difference between them. You're losing delta Z. But the total energy doesn't change. And remember that the total energy and the specific energy, the difference there is whether you're measuring against some horizontal datum. It's the delta Z that we talked about. So let's look at this, first of all, in graphical terms, because that makes it easy to understand what's happening and why. I don't think I have this one animated like I did the other one. We start off with Y1. We go over to our curve and down, and here is the energy that's associated with our initial depth Y1. And in this case, it looks like they're saying that this is a subcritical depth, because here's our critical depth, and it's above the subcritical depth, and so we're in the, it's above the critical depth, so we're in the subcritical range. Now, we move to the left because energy is being lost in our delta Z. So the step up moves us to the left in the amount of delta Z, and now here we are at E2. And there are 2 possible crossings, and so it could be a supercritical depth or a subcritical depth, but we choose the subcritical, and we go back over, and that tells us what the new depth Y2 is going to be. So the step up actually makes the flow more shallow. So that's what they're depicting in the figure here is, you know, the water was deep and it gets shallower. And if it's getting shallower, that means that the velocity increases. So the velocity has to go up to get that same flow rate Q through a smaller cross-sectional area. But like I said, there's a limit, right? There's a delta Z max after which you can't accommodate the flow anymore. So look at this specific energy diagram. What do you think the delta Z max is? If we're starting at E1, what's the maximum delta Z that you could have and still be able to get the flow over that obstruction without it starting to pool and back up and like choke upstream? It's until you get to this last little point here, the point that's associated with the critical depth. And so the maximum delta Z would be from E1 to there. So it would be the distance along this axis that's associated with the critical depth. And remember what I said at the beginning of the lesson was that critical depth is the depth associated with maximum efficiency. It's where you can get the most flow rate for the least amount of energy. And so when your last little bit of energy that can still get the flow through there without obstruction, that corresponds to the delta Z max. Okay, but the rule of thumb, if you want to make a list of them, is that if you've got a step up and it was subcritical, it's still going to be subcritical, but the flow depth decreased because of the delta Z towards the left. We lost energy, so it's less deep than it was before at Y1. Any questions about this? What if the flow is supercritical instead of subcritical? So we can just jump through the diagram here. Starting at some depth Y1, you go over to the curve, down. To the left delta Z, when you've got a step up, you go to the left, back up, and over, so it actually gets deeper. The Y2 is greater than Y1 if we had supercritical flow that went over some obstruction. We're still in the supercritical range, though. The new depth is greater than the old depth. All right, so let's try this one. We've got a step up in this example with a flow rate of 250 cubic feet per second. We know the bed step up is half a foot. We want to find out what will be the flow depth after this step. We're going to use the same process as we did with the step down. We want to analyze the Froude number to find out if it's supercritical or subcritical. We're going to find the velocity, and so on. So V1 is Q divided by A1, and the area here is 50. The Q is 150, or is it 250? Okay, so it's 250 cubic feet per second divided by 10 by 5 at 1, so 50 square feet. So the velocity is going to be 25, so 5 foot per second. All right, and since this is rectangular, let's try finding the critical depth and assessing the flow regime by that. So the flow per unit width, Q divided by lowercase b, is 250 cubic feet per second divided by 10 feet of channel width. So that's 25 feet squared per second. Therefore, we can find the critical depth y sub c by lowercase q squared divided by g to the 1/3 power. And so that is the 25 feet squared per second. And that quantity squared divided by 32.2 feet per second squared to the 1/3 power. So what we'll get is that the critical depth is 2.69 feet. So the flow condition at 1, is it supercritical or subcritical? We know that y1 is 5 feet, and yc is 2.67 feet. So y1 is greater than yc, thus it's subcritical at 1. Okay, so we've got subcritical flow. Now let's find the energy at 1. The energy at 1 is 5 feet, because that's the depth, plus the velocity head. 5 feet per second squared divided by 2 times 32.2 feet per second squared. So it's 5.388 feet. The way that I described it on a previous slide is the energy at 1 is how much we've got to get over the obstruction, how much we've got to get over this step. So we had a flow, there's a step up, so we want to find out how is the water level going to change. We had a y1 which was 5 feet to begin. We want to find out what is y2, and our step up here, the delta z that we're dealing with, is 1.5 feet. Right? Oh, 0.5. 0.5 feet. Okay, so at 1, the energy at 1, that's what we're going to use to try and get over that obstruction. It's like speeding up before you go up a hill, kind of. Although it's not speeding up, it's just how much energy it has to get over the obstruction. So the E1 is 5.388 feet. And what we know is that we have to set that equal to, so the 5.388 feet is how much we've got available to go into the depth at 2 plus the velocity head at 2 plus the step. So that energy has to go into it's got to overcome the step, establish a new depth, and have a velocity head. Okay, so based on the flow rate that we've got of 250 cubic feet per second, and the a squared is going to be in terms of y. This term will be 9.705 divided by y squared. When we put in that area, area is going to be 10 times y, whatever the depth is, and g is 32.2. So what we end up with is 4.888 is equal to y2 plus 9.705 divided by y2. Okay, so the 5.388 minus the 0.5 feet is where the 4.888 comes from. And the same as before, we're going to multiply each term by y2 squared. Okay, because area it's area squared, so this is actually y2 squared in the denominator. y2 squared. Any questions so far? Okay, so this goes to y2 cubed minus 4.888 y2 squared plus 9.705 is equal to 0. Okay, so same as before, we'll get 3 roots. One of them will be negative, one of them will be supercritical, and one of them will be subcritical. So y2 can be negative 1.28 feet, it can be 1.762 feet, or 4.383 feet. And since we had subcritical before, we'll have subcritical after the step, and so that this is the new depth after the step. You're drinking from the fire hose today. Getting a lot of information in a short amount of time, although maybe it doesn't feel like a short amount of time to you. It does to me. Time flies when you're standing on this end of the classroom. I'm getting exercise. I get to walk around. It's easy to stay awake. You've got belly full of sandwich, right? All right. Any questions? How do you find the flow depth? So a couple of reminders that we can always use this formula on the left to find the depth at critical, to find the critical depth. We can use the one on the right for a rectangular channel. Here's an interesting thing, is that when you've got critical flow, the water depth is 2/3 of the specific energy. The other 1/3 of the specific energy exists as the velocity head. So if I go back to the first diagram, the first new diagram that I showed you today, this critical depth is 2/3 of the total specific energy. Yeah, the velocity head is 1/3 and the depth is 2/3. Okay, so if you've got a rectangular channel and 50 cubic meters per second is going through a 5-meter wide rectangular channel, just as a reminder, you can find the flow per unit width Q. That would be the 50 cubic meters per second divided by the 5 meters wide. And so the flow per unit width is 10 meters squared per second. And so the critical depth is going to be the 10 meters squared per second squared divided by 9.81 meters per second squared. All of that to the 1/3 power. And so you can find the let's see, yeah, here it is. The critical depth, 9.81 divided by to the 1/3 power, 2.17, right? That's what you got? 1.7 meters. And so what we're saying is that when it's critical conditions, the energy at this state is just 3/2 times the critical depth. So when you've got critical flow, it's easy to find how much specific energy there is because you just multiply it by 1.5. And so the total energy is the specific energy is 3.252 meters. And how could we double check that? Remember that the energy is the depth plus the velocity head. So we could find what the velocity is at that condition. And so the flow rate was 50 cubic meters per second. The cross-sectional area would be 5 meters times the depth, 3.252. So, oh, you're right, 2.17. Thank you for noticing that. Right. What I had written there was the total energy. It was the energy, not the depth. So let's just make sure that this little rule of thumb actually does work. So 2.17 meters, 5 times 2.17 and 50 divided by that. Okay, so the velocity should be 4.608 meters per second. And so then the velocity head is that squared divided by 2g. So the velocity head would be 1.082 meters. And then the depth that we had was 2.17. And the sum of the two together is 3.252 meters. So it works out that, and only works out for critical conditions. I guess this is the second most common mistake in open channel flow. I told you that sometimes students forget you should only use this formula for a rectangular channel. The other formula that gets misapplied is that energy is always 3/2 of the depth, and that's not true. It's only 3/2 of the depth when it's critical depth. Then you can find the specific energy that way.
You have a supercritical drop.
Sure. You mean like a supercritical flow and then there's a drop?
Yeah.
Yep.
So does that mean the depth will be?
It'll decrease. Yep, it'll get even lower. So let's go back to the slide where we were looking at drops. That's a step up. Yeah, so the question was, can you have supercritical flow and then it drops? So if you had supercritical flow, here would be your Y1, and then the drop would mean that you're moving to the right, and so it would get even shallower, just as you said, instead of deeper. Other questions? All right. So in review, there is, what equation do we use to find the new downstream depth? Well, we set the specific energy equal to each other, and then the energy at 2, in this case on the left, is energy at 1 plus the delta z. And in this case, the energy at 2 is the energy at 1 minus the delta z. So that's how we find out, the specific energy increases in the case of a drop, and the specific energy decreases in the case of a step up. All right, we've just got a couple of minutes remaining, so I want to introduce this concept of the maximum step and what happens if we go beyond it. So let's say that we had subcritical flow upstream of the obstruction. So we had subcritical flow at 1, and we've got some step up, and so the flow gets shallower. We already know that that's the trend, is that the flow gets shallower when it was subcritical and there was a step. So what if we made it a bigger step? Here in condition B, it's still subcritical flow at 1. We just wanted to see how is the water going to respond if we make that step a little bit bigger. So what did the water do? Well, the depth got a little bit shallower. This Y2, it got even smaller than the transition before. And now we've gone so far with our critical step, we've made it just so big that now the depth downstream is the critical depth. Now you're starting to understand where critical depth gets its name, is because this is like the critical transition point, that if we made this step any taller, then the water would start to pool upstream. It actually starts to choke the flow temporarily so that the water depth can increase until there's enough energy to get over that larger obstruction. Right here, when you get to this point, this is the largest obstruction that the water can get over. It only has enough energy at 1 to get over this obstruction. And so when you're at that critical point, you've got the critical depth is the flow depth. If you need to find the specific energy, well, it just happens to be 3/2 of the critical depth. So if we went beyond that, a step larger than the critical depth, then it introduces a new nomenclature for us. So there's this y prime of 1. And y1 is the depth that there was before the step. Y prime of 1 is how much deeper the water gets because of the step. The water will pool until it finally has enough energy to get over that new obstruction height. Because this is a really big step here. This delta Z sub D, this is a big one that's larger than the critical step. And so E prime of 1, that means how much energy is needed to get over this new obstruction. Backwater, yep. It'll cause the water upstream to get deeper.
We're talking about the water that's ahead, but not being deeper.
You're saying the water this way?
No, the water, because of the rise of the step, caused water to travel.
To go that way?
Yes.
No. It's just that the water that's going towards it will slow down as it gets deeper. And then when it's finally deep enough that the water can flow over the obstruction at the critical depth, then it keeps going. It reestablishes steady flow. So it's unsteady for a little while. So this is where we're going to pick back up when we get together on Tuesday after spring break. Hope you guys have a great vacation. I'll see you 9 days, right?
Either start now or wait.